Today I will be discussing Lab 3 of Physics 1, which is the black hole lab. So first, the purpose of this lab is to use forces that are observed in a computational model on GlowScript of a star moving around a black hole and then determining the mass of that black hole. And the reason that this is important is to demonstrate that observations such as this in nature can be used in order to find something that would otherwise be unknown, which is actually very cool. So the question is, how are we going to be able to do this? And in order to explain that, we have to understand a few concepts. And those concepts will be Newton's second law and Newton's universal law of gravitation. And I also included this image just so that you could see how Newton's universal law of gravitation actually works upon an object. And this isn't a black hole, but it does demonstrate the gravity that pulls the path of the moon around the Earth. So for this lab, we need to know Newton's second law in order to know that F net will be equal to dp over dt, which is the change in momentum, in order to find the unknown forces of this star around the black hole. And then universal law of gravitation is going to be used to solve for the unknown mass, and that's going to be equal to the F net is equal to the gravitational constant times the mass of the star times the mass of the black hole divided by the distance between them squared. And the gravitational constant I have down there is 6.7 times 10 to the negative 11. And then using that formula, we essentially just solve for the mass of the black hole. So here's just some assumptions that I wanted to put out there that we are making, the mass of the star being equal to 2 e to the 30 grams, and then we're assuming that we're looking at the time interval of 1 Earth day and that the agent that we are orbiting around is at the origin and that the total force is due to a single gravitational force. So we're assuming that there are no other forces acting upon the object, which we would need to assume in order to actually find this mass. So here's the overall procedure that we took during the lab, which was writing the code in GlowScript to model the star's orbit with given data. And this is going to be different for everybody because it was based off of our GT emails, and then calculating the momentum, net force, and their components using the Newton's second law, which I just explained, and calculating the radius from the difference in the star and the black hole position. So that's the next step. And then the final step will be using that universal law of gravitation to finally determine the mass of the black hole. So here is my code in GlowScript. So this is actually my completed code, so it's already been edited. And the first thing that was done in this, as you can see, is calculating that velocity and momentum. And then going down, just as you heard from Newton's second law, we're going to use that change in momentum to find dp dt and ultimately that net force. And then we had to go on to calculate the parallel component of F net. To understand the slowing or the speeding up of the object in the parallel position, and then calculating the perpendicular motion to understand the curving motion of the star. So here is the final piece of my lab where you see in the code where I actually solved or estimated for the mass of the black hole using a derivation of Newton's equation of universal gravity. And I found the mass of the black hole to be about 7.59742 times 10 to the 33 grams. And this was estimated by taking what I found in GlowScript and averaging those. And so in conclusion, what does this mean? So the question poses in the analysis, discuss the net force and its parallel and perpendicular components and how these are different from the rate of change momentum and its parallel and perpendicular components. So we calculated the parallel to see the speeding up and slowing down, and the perpendicular to see the curving motion like I explained before, and the net force equals the vector sum of its parallel and perpendicular components and will point in the direction of the resultant vector. The net force and its components are the causes affecting the corresponding rates of change of momentum in its components, as you can see in that equation. And if the black hole whose mass that we found was removed and a different black hole is placed in the same position, assuming that nothing else was changed, could you tell the difference? And my conclusion would be that if the data remains the same, so not a change in mass or a change in force, this would mean that the causes must also be the same, so therefore the mass of the new black hole would not be any different than the original one that we found per the model for this lab.